In this chapter, we introduce regular expression, regular sets and representation of regular sets using regular expression, operations of regular expression along with the identity rules which are described, equivalence of finite automata and regular expressions are explained here. First of all, we'll see the learning objective of regular expression and regular grammar. Regular expressions are the notations to describe a language. This is used to represent the language. It is a powerful tool in search engines. And it is a language tools like Lex, VA Editor, PHP, Perl, etc. It makes the student to understand the notations of regular expression and makes them to use the regular expression to describe many programming languages. First we will see the definition of regular expression. Regular expression describes the language accepted by finite automata. It is useful for representing certain sets of strings in an algebraic fashion. It is any terminal symbol or element of alphabet is a regular expression. Example, phi MT A is in alphabet. Then phi is a regular expression that denotes the empty set. And then empty symbol is a regular expression that denotes the set of empty. A is a regular expression that denotes the set of A. Next we will see the operations of regular expressions. There are 4 types of operations. One is union, next one is concatenation, and third one is cleanly closure, and fourth one is positive closure. The closures are of 2 types, that is cleanly closure and positive closure, which is also called as iteration. First we will see the union operation. Union of 2 regular expressions R1 and R2 is regular expression or, that is R equal to R1 plus R2. For example, let A be a regular expression of R1 and B be a regular expression of R2, then A plus B is also a regular expression of R having the elements A, B. Next one is concatenation of 2 regular expression R1 and R2, which is written as R1 dot R2, which is also a regular expression of R. For example, let A be a regular expression of R2 and B be a regular expression of R2. Then A dot B is also a regular expression of R having an element AB. Union operations are represented by plus symbol. Concatenation is represented by dot symbol. Next we will see the iteration or closure of a regular expression, which is written as R star, is also called as regular expression. If A be a regular expression, then MT, A, AA, 888 goes on is also a regular expression. The language of this regular expression or is represented as, for cleanly closure, it is represented as L power star is equal to union I is greater than or equal to 0, that is I is between 0 to infinity, then L of phi. Then positive closure is represented as L plus, which is equal to L power I, where I is equal to 1 to infinity, that is I is greater than or equal to 1. If R is a regular expression, then R power star is also a regular expression. The cleanly closure star operator. The cleanly closure of a language L is L power 0 is equal to empty. L power 1 is having some alphabet, that is W, and L power 2 is having W1 and W2, where W1 belongs to language, W2 is also belongs to language. Therefore, L power I is equal to W1, W2, etc. up to Wi. All W's are chosen from the language. So, we say L power star is equal to L power I, where I is greater than or equal to 0. That is, I is between 0 to infinity. For example, we can see L is equal to 1 comma 0 0. Then L power 0 is equal to empty. L power 1 is equal to 1 comma 0 0. L power 2 is equal to 1 1 comma 0 0 comma 1 0 0 0 and then 0 0 1, etc. goes on. L power 3 is also represented here. Finally we say L power star is equal to L power 0 union L power 1 union L power 2 union, etc. goes on. Therefore L power star is equal to L of phi where I is greater than equal to 0. Similarly, we can derive L plus is equal to L power I where I is equal to greater than or equal to 1, since L plus will not include empty here. Next we see the algebraic laws of regular expressions. There are 7 laws. One is commutative law, associativity law, identity law, annihilator law, distributive law, idempotent law, and cleanly closures law. First one is commutative law. Commutative law says if E and F are a regular expression, then E plus F is equal to F plus E. Then associativity law, E plus F plus G is also a regular expression, is equal to E plus F plus G. And then EF into G is equal to E into FG. Next one is identity law. Identity law, E plus phi is equal to E, empty into E is equal to E into empty is equal to E. And then annihilator law says phi into E is equal to E into phi is equal to phi. Next one is distributive law. Distributive law says E into F plus G is equal to EF plus EG. F plus G into E is equal to FE plus GE. Next one is idempotent law. That is E plus E is equal to E. Any regular addition of any regular language will give you the regular language itself. Next one is cleanly closures. E power star is equal to E star. 5 power star is equal to empty. Empty power star is equal to empty. E power plus is equal to E into E power star. Using these laws, the regular expressions can be simplified. Next we will see the equivalence of finite automata. The regular expressions on finite automata are equivalent in their descriptive power. The equivalence can be shown by mathematical inductions. Here, regular expression can be converted to a non-deterministic finite automata with empty moves. The NFA with empty moves can be converted to NFA without empty moves. The NFA without empty moves can be converted to a DFA, that is deterministic finite automata. This can be again converted to a regular expression. These are the equivalents of regular expression and finite automata. Next we will see how to convert the regular expressions to empty NFA. That is how to convert the regular expression to empty non-deterministic finite automata. We have proof, which is a induction on the number of operators, that is union, concatenation and closure, that is plus dot star in the regular expression. There are 3 inductions. First we will see the basis of the induction, that is if you have symbol A, it moves from one state to another state using A. If you have empty as a regular expression, then using empty it moves from one state to another state. If you have phi, that represents there is no transition between the states. So this is the diagrammatic representation of this one. Next we will see the first induction. First induction is the union. We will represent by U operator or plus operator. It shows that we have 2 regular expressions, that is E1, and 2 regular expression, that is for example A and B. Here we have the induction for union, that is E1 and E2 are the finite automata having some states, alphabets and transitions, and E2 also have some set of states, alphabets and transitions. Then E1 union E2 is represented by this diagrammatic way. This shows that whether it goes through E1 or it goes through E2. For example, if you have regular expression A plus B, then it shows that it goes through A or it goes through B. Finally, reaches the final state by going through the state A or by going through the state B. Next one is the induction 2, which is a concatenation operation. In concatenation operation also we have E1 and E2 as a finite automata, which are both of the finite automata consists of some set of states, alphabets, transitions, initial state and final state. If you have regular expressions OR, then OR will be equal to R1 and R2, where R1 and R2 are the concatenation of two regular expressions. Here this is the graphical representation, diagrammatic representation of E1 and E2. It should goes through both E1 and E2. So we have finite automata for E1 and we have finite automata for E2. Both of them are connected using the empty symbol. Next we will see the third induction 3, that is closure. Closure is a finite automata which has some set of states, alphabets and transitions. Here we have, if you have regular expression A star, that it will have empty, so from initial state goes to final state directly, and it have A, it goes on like this. So the finite automata will be repeated, that is using empty the loop repeats. This is shown in here. Using these three inductions we can construct a NFA with empty moves for a regular expression. Here we have an example 0 plus 1 power star, 0, 1 and 0 plus 1 power star. 0 plus 1 uses the induction 1, that is using 0 it goes to final state, or using 1 it goes to reaches the final state. That is represented by using induction 1. After drawing 0 plus 1, diagrammatic representation of 0 plus 1, we have to construct 0 plus 1 to the power star. That shows that it should goes to the final state by using empty, or sometimes the loops also gets repeated. This uses the induction 3. And then after computing 0 plus 1 power star, we have to concatenate with 0 and 1, which can be concatenated using the induction 2. Again 0 plus 1 power star we have, which is already derived, that can be placed here. So this is the graphical representation of 0 plus 1 power star, 0, 1, 0 plus 1 power star. This is the empty moves with of NFA. So the regular expression is converted to empty NFA. This is the example. Likewise, we can also derive NFA for any regular expressions. So far we have seen what is regular expression and what are the operations are there in a regular expression and what is the laws